The next learning objective is all about Newton's first law. Let's read it together. I can use Newton's first law to correctly explain a physical phenomenon in terms of the causality between net force and acceleration. So it's this idea that somehow net force is correlated with acceleration. There is a relationship between them. It's not just correlation, actually, it's causality. Net force causes acceleration. And it's not the other way around. Acceleration doesn't cause net force. Let's define what Newton's first law is. First off, there are three Newton's laws of motions: first law, second law, and third law. The first law, I'm going to give two different definitions because I find that the definition most famously known can be a little bit confusing in its application. So I'm going to give one that's much easier for the application side of this. So the wiki definition, or the definition you would find if you looked it up, is that a body remains at rest or in motion at a constant speed in a straight line, except insofar as it is acted upon by a force. That is a definition I looked up when I looked up it on Wikipedia. I would argue that they should have been more clear about what a force is, not just any force, but specifically an external force. Not just any force, but specifically an external force. My definition for this is going to be easier for us to use in the classroom, and that is, if there is a net external force, then an object will accelerate. And if an object is accelerating, there must be a net external force. So in math, we can show this a couple ways. So if a equals 0, so if the acceleration equals 0, then the sum of all forces, which remember is the definition of net force, must equal 0. And this is the sum of all external forces. If the sum of all forces equals 0, then acceleration must be 0. So it works both ways with this. Acceleration doesn't cause net force, but it is true that you could say, if something is not accelerating, then there must be no net force. And if something is accelerating, so that's in the case of if acceleration is not 0, then there must be a net force. So the sum of all forces must not equal 0. And you could also say it the other way around. If you happen to know that there's a net force, then you will know with 100% assurity that the object must accelerate. Let's look at an example. So if you have a box on a table and the box is at rest and does not start moving, so it's at rest and stays at rest, what is the net force? Well, before we even draw anything, we can know for sure that since acceleration equals 0, then the net force must equal 0. That's how you apply Newton's first law. That is what Newton's first law is about. The idea that you can look at a situation and just ask yourself the question, is it accelerating? If it's not, then net force is 0. If it is, then net force is not 0. Let's draw the free body diagram though for this box. So we know that there must be a force of gravity acting on this box going down. And we're just going to label that Fg. If this was the only force acting on this box, then the net force would not be 0. But we know that since it's not accelerating, there can't be a net force. The net force must be 0. So there has to be some other force that is going against the force of gravity, that is canceling out the force of gravity, such that when you add them together, you get 0. So that force is what we call the normal force. So just drawing that right there. And we put an N for that. Normal force, those two vectors are the same length but opposite direction, meaning that they would cancel each other out perfectly and get a net force of 0. This is essentially the contact force. The table is pushing back up on the box. And that's actually the fundamental idea behind Newton's third law, is that the box pushes on the table because of gravity, but the table pushes back on the box. Equal and opposite reaction is the phrase that you would often hear for Newton's third law. Looking at another example, let's say we have a skydiver and jumps out of a plane. We're going to analyze the motion of the skydiver at the beginning, middle, and end of their jump. So when they just jump, and we're going to ignore the fact that they might be moving horizontally. Because remember, the two perpendicular directions, we can consider them separately. We can consider them independent of one another, because they are. In the beginning, there is just the force of gravity acting on this skydiver. And we know that they are accelerating because they don't start moving very fast down, but then they start picking up speed. So there must be an acceleration, and that acceleration must be in the downward direction. So there must be a net force pointed down in the beginning. This is going to be one of the rare cases that we're actually going to consider air resistance because it's really important to how we can jump out of a plane and not hit the ground going Mach 5. As you pick up speed, you're going to have drag, and that drag is going to increase. Eventually, the drag is going to get to the point where the magnitude of the drag force is equal to the magnitude of gravity. Under this circumstance right here, so actually let's backtrack. Over here, acceleration is not equal to 0. And therefore, and that is because of the sum of all forces is not equal to 0. That was in the beginning where we didn't have drag. But now, under this certain circumstance, we have the sum of all forces now equals 0. And therefore, the acceleration must equal 0. So now this person is no longer accelerating. Whatever speed they got to during their fall, they're going to stay at. This actually has a special term called terminal velocity. The speed at which you hit when you're going through a drag force, such as air resistance, and you reach your maximum speed, this is terminal velocity. So skydivers don't continue picking up speed. They only pick up speed to a certain amount of, velocity before they stop going any faster. Then let's take a look at a later portion, maybe not the very end, because the very end is them landing on the ground safely. But we're going to take a look at a later portion where they've just opened up their parachute. So they've opened up their parachute. We know that when they open up their parachute, they're going to suddenly stop going as fast. They're going to suddenly have an acceleration. So there must be an acceleration. Acceleration is not 0. In fact, the acceleration is going to be upwards because it's going to slow the person down. So that means the sum of all forces also can't be 0. What that means is that the length of these two forces cannot be the same. So drag must be greater than gravity. In order for this to slow the person down and for there to be a net force and therefore an acceleration, drag must be greater than gravity. Here are 3 conceptual practice problems for you to practice applying Newton's first law. The first one is in the sport of curling, the idea behind curling is that players send these stones down an ice field and they glide, but eventually they do stop. And the idea is you're trying to get closest to the center and you can knock each other's curling stones out of the way. Draw the free body diagram for the stones sliding across the ice and use Newton's first law to justify why you drew it the way you did. So draw the free body diagram, but then explain why you draw it the way you did. Next one, a book is resting on a table, situation we've talked about in this video. But describe what would happen to the book if the table is suddenly pulled out from underneath it. So suddenly there is no table. Explain how this scenario illustrates Newton's first law of motion. So why does this show Newton's first law of motion? And then lastly, a passenger in a car feels pushed back into their seat when the car suddenly accelerates forward. Explain this sensation using Newton's first law of motion. Describe what would happen if the car suddenly stopped. What would happen to the person, and why does that show Newton's first law is being applied?